Welcome back, ladies and gentlemen. Here we are with the last video of the chemistry unit. It's taken us some time and we have covered a lot of ground. Now, before we get directly into that final lesson, let's take a look at just how far we've come, because you've covered an awful lot. Up here, we've got the start of a question that you know how to answer at this point, one that you have worked through diligently and carefully many times before. But how much feeds into this question? Mg. We know what Mg means. We know that Mg here means this is magnesium. We know how to turn symbols into words. We know that this O, well, this is oxygen. But it's not just any oxygen, because there's a 2 there, which means we know it's oxygen gas. It's a diatomic. A diatomic, 2 atoms, which comes about because this is a non-metal that can share. And that sharing of electrons creates a unique bond when there's no other options. And there are no other options, at least at first. But now that we've put these two together in a chemical equation where we are attempting to make some kind of product from these reactants, a chemical equation that we no doubt could make from the words, right? Magnesium combines with oxygen gas. I could say that, and then I could ask you, what does that make? And you could tell me. You could look at that and go, I know what's going to happen, because this is very clearly a synthesis reaction. And if it's a synthesis reaction, which we can tell because 2 simple things are combining together to make one more complicated thing, then you can look at this and go, I know what's going to be created. It's going to be MgO. And you know that's what's going to be created because you can take that and go, I know how this is going to work, because Mg is a metal and O is a non-metal. And Mg is going to be, of course, good old 2+, and oxygen is 2-, and we know that because of where they are located on the periodic table. Magnesium is, of course, right here, give or take. It's 2 spaces, 1, 2, away from the end, and oxygen is about right there or so, 1, 2 spaces to the end. So that means that you get 2+ and 2-, which means, of course, when you put these together, they balance perfectly. The full transfer of electrons is possible because there are 2 spaces, and each of these will move in to fill those spaces. So this is the final way to write that product. And yet you also know that you're still not done. Because a question like this, you know from the conservation of mass, everything must be equal. The left and the right must have the same number of atoms. So you end up looking at this and going, well, I've got 2 oxygens here and only 1 here, so I need a coefficient out front. And that means I have 2 magnesiums, so now I have to put a 2 here. All because, of course, of the conservation of mass, which makes the left and the right equal to each other. This is the sum total of everything that you have learned, everything that you have put together in this unit. You have learned how to understand, how to read the periodic table. You have learned how to assemble these atoms and molecules. You have learned how to convert them from one into another. You have learned about sharing. You have learned about transferring. You have learned about mass and how it's conserved. You've learned different types of reactions. You've learned all these different things. Each one of these building one on top of another. You have come a long way up this mountain of knowledge. But we're not done yet. I know. There's still one more. On the plus side, this one extra thing is kind of disconnected from the rest of this. I mean, it's going to use names and symbols and the idea of transferring and the periodic table is going to happen. Conservation of mass still applies. So a lot of this stuff is still going to be important, but not directly. This doesn't build off it. We're not going from writing the letters of chemistry to writing the words of chemistry to writing the sentences of chemistry, and we're not now going into paragraphs. You guys aren't ready for paragraphs. That's 11 and 12. But we are going to continue to increase our dictionary, to increase our thesaurus, to have better words and ideas to talk about. And that's going to be because we're going to talk about acids and bases. How's that for a really long intro? So, for acids and bases, what are we going to be seeing here? Well, acids and bases are sort of a binary choice. We've seen binary choices before, right? It means there are two options. And much like with, say, the types of reactions or the families on the periodic table, acids and bases are what we would call a category. They're a category that we invented in order to understand and catalog different chemicals that we found all over the world. Now, the purpose of doing that, of course, is like any category is it makes things easier. Once you know the category, you just go, oh, okay, you fit in this category, that means you're going to do all of these things. And that's it. Now, this particular category is pretty broad, right? There are a lot of acids, there are a lot of bases. Some of them are incredibly dangerous. Some of them are super tasty. Yes, tasty. That's not the thing you expect to hear in chemistry, but here we are. Either way, we're dealing with materials that you will see in your everyday life and in the lab. My advice, eat the ones in your everyday life, but not the ones in the lab. Now, acids and bases, as mentioned, have opposite and related properties. So we're going to have acids, we'll put them on this side over here. Okay, and we'll put bases right here. All right, let's do this. First things first. What do they taste like? That's the thing you want to know. I mentioned that they have a taste. What do they taste like? All right. Taste. Now, why in the world does taste come up at all? Like, at no point for the other categories did I tell you. I didn't tell you what a halogen tasted like. I'll give you a hint. It tastes like death. I didn't tell you what a combustion reaction tastes like. I'll give you a hint. It tastes like fire. We didn't talk about those because, generally speaking, those things don't go in our mouth. So why do acids and bases go in our mouth? Well, turns out that's the number one way that we identified them back in the day. As you're going to discover as we go through this lesson, there are all sorts of ways to identify acids and bases now. But when we started, we only had our eyes, our ears, our hands, our nose, and our mouth, which meant that in order to understand these things, we had to use the senses that we had available. And many acids and bases, you look at them and they look identical. They sound identical. They feel different, which we're going to see in a second, and they taste different. So an acid, I will tell you right now, tastes what we would call sour. You ever had those sour candies, right? Like the, I'm trying to say, cinnamon hearts, yeah, a little bit those, the sour worms or the peach candies. Those are sour. Now, bases, I said, are equal opposite. So what's the opposite of sour? It's not really sweet. It doesn't really match. The opposite of sour, well, think about what sour makes you do, right? You eat something sour and you go, ooh, right? You pucker. Well, when you eat something that is the opposite of sour, you do the opposite. You get as open as possible. You want to get rid of it. You're like, ugh, get it off my tongue. So what is a base? A base is bitter. An acid is sour and a base is bitter, and that's how we tell the difference between the two. In the old days, chemists would take an actual sample and they would take a little bit and just put it on their tongue. They'd be like, oh yeah, that's an acid, all right. And of course, if it was too strong an acid, they wouldn't have a tongue very long. Yeah, accidents happened in the lab. There's a reason why we have so many rules about you're not allowed to eat or drink anything. I mean, in the old days, the chemists used to break them all the time because it was the only option they had. But there was an art to learning how to taste these things without getting yourself in trouble. Now, I mentioned we've got 5 senses. Generally speaking, sound and sight aren't going to help, but taste did, and so did touch. Acids have a certain way of feeling. If you put them on your skin, if you spill an acid on your skin, now think back, think of cartoons, think of movies. When they have an acid on screen, what does it make you think of? How does it behave? What do you see? What does it do? Why, it burns. It burns. The other thing we could say is that it feels sharp. Very sharp. When you spill an acid on yourself, it will sting. It's like 1,000 needles jabbing into you, and that's only if you still have your nerves when you're busy feeling it. Sometimes it does a lot more damage. So you feel it as it burns. Well, what's the opposite of burning? What's the opposite of sharp? Is it cold? Well, not really. The opposite of sharp, the opposite of burning in this case, is that most bases actually feel slippery. Most bases actually feel slippery. They glide on your hands. Now, this is going to come up with the fact that you've got some examples of these, right? Okay, I already gave you some examples of this. You've got stuff like sour candy and things, lemons. What's an example of something that's bitter or slippery? It's a little bit trickier. What's something that's bitter and slippery? Soap. An example of an acid would be things like vinegar. Whereas a base is going to be something like soap. You're going to see, of course, that there are a lot of different options of acids and bases beyond vinegar and soap, but those are some 2 good ones to pull out as an example. So you've got yourself some vinegar, you've got yourself some soap. One of them is sour and sharp. Right? If you get a little vinegar in your eye, you get a little acid in your eye, oh, it'll feel sharp. It'll feel very sharp. But soap is slippery. It just slides on your hand. Why? Well, it has to do with how these 2 react. You see, the way these 2 react, we said burn, but that's not really accurate. The reason it feels like burning to us is because our skin has, of course, nerves that feel things, but our skin has sort of limited nerves. They can do a lot, but they don't have the full range of possibilities. That's why we can see a lot better than we can touch, right? Our eyes, very sensitive. Our skin, sensitive, but not able to tell the difference between 2 different things very easily. So we actually have a word to describe what an acid does. What we do is we talk about how it reacts. And what we see is that an acid is what we call corrosive. And what that means is a type of reaction. So we might have, let's say, an acid, HCl, excellent acid, very destructive, plus some magnesium. And what's that going to do? Well, take a look at this. You know what's going to happen based on your understanding of chemical reactions. This chlorine, it's a non-metal. It's going to combine with the magnesium that's a metal. So you're going to end up with something like magnesium chloride. Now, got to balance it, so that's a 2. And then I've got some hydrogen gas floating away. This is a pretty standard type of acid reaction. It's a corrosive agent. It'll eat away at things. That's usually how we describe it. And it has this sort of tendency here, because you'll notice that the H, that's a key feature of acids. This is kind of how we identify a lot of our starting acids. Now, fun fact, you're going to see going forward that it's a little more complicated than that, but for the moment, we're going to say that acids have got a hydrogen in it, right here. And this hydrogen is going to react with the acid. It's going to pull things apart. That's how the acid is going to work. It's going to pull things apart. Well, in this case, what we see is that this corrosive agent is going to eat a metal. Eat with little quotation marks there. It's not eating it. It's corroding it. That's literally what the word means, corrode. To eat away, to dissolve, to destroy in some manner, to consume. And that's what it's going to do. It's going to eat this metal. It's basically a single displacement reaction of the metal itself. But what about bases? Well, they're equal and opposite, and they have a word, although people don't usually know it. Corrosive you might know. But this one you probably don't know. Caustic. A base is caustic. It doesn't burn. It makes everything slippery. But why? Well, let's take a look at its chemistry. A base, a classic base, NaOH. Almost all the bases that we're going to talk about are going to have this OH in it, just like how almost all the acids that we're going to talk about, as I just said, have got an H in the front. Hydroxide, of course, is a non-metal. Well, it's a pair of non-metals. It's a polyatomic, but it's negative. So if I take hydroxide and I add it with, say, I don't know, sulfur, well, what's going to happen, right? The sulfur and the hydroxide are going to switch. So I'm going to get Na2S plus OH. Now, there's going to be some side reactions that happen as well, because usually this all happens in water, but don't worry about that right now. Let's just look at this simply. This is a single displacement reaction where we are displacing the non-metal. Right? You can imagine I have a brick of sulfur here, and the corrosive agent, the base, pulls the sulfur off and replaces it with an OH. And if there's enough base, it'll do that to all of the sulfur. It will get rid of it. So in some ways, you can say that this eats nonmetals. So herein is the question. Why are bases slippery? Because you're mostly a nonmetal. So a base eats you. One of the ways in which a base attacks the human body, which is very unpleasant, is that it will dissolve away the fat layer underneath your skin. And in a process called saponification, it's the way you make soap. And it will turn the fat deposits into soap, making your hand slippery. If the base is strong enough, it'll dissolve everything, which is a little lethal. Of course, it'll also be caustic. Corrosive is over here. It'll also be caustic to the rest of your tissues as well, your skin, nails, hair, everything. Not a pleasant thing. Not a pleasant thing. Do not recommend. But that's where this is going. Now, that doesn't mean you need to panic. Soap isn't going to dissolve you unless you're the Wicked Witch, but then that's mostly water, not soap. Soap that we use to clean is not a very strong base, just like how vinegar is not a very strong acid. What does that mean? Weak, strong, weak, strong. That we have to understand. So a few things that we can just summarize here, right? Sour versus bitter. Sharp versus slippery. Vinegar and soap, those are some examples. We'll talk about a few more in just a second. Corrosive and caustic. Corrosive tends to target metal. It'll still hurt you. Don't drink anything too strong. And caustic tends to eat non-metal, but again, it can attack metal as well, but it's got a preference. The chemistry behind attacking metal is a little more complicated. And here are some examples of some formulas. Now, the thing here is, of course, again, as I said, the strength. So what do I mean by strength? Well, it turns out that you can't just point at something and say, oh, that's an acid. Well, that must be very dangerous. Because, as I mentioned, vinegar, it's not really that dangerous, but it's an acid. It tastes sour. Yeah, everything that tastes sour is an acid. But they're not all dangerous, not by any stretch of the imagination. So we needed a way to gauge how dangerous stuff was, how strong it was, what could it accomplish, what could it do? And we came up with a scale. Now, the scale is called the pH scale. P in this case stands for power, and H stands for hydrogen. So it's the power hydrogen scale. So basically, how strong is the hydrogen? And what you see is that the scale is it's a weird one, to put it mildly. It's a weird one because the scale is centered not on 0, but on 7. The reason for that has to do with the mathematics behind its creation. It's a little bit confusing, but what it means is that something that is located at 7 on the pH scale is considered neutral. So it has neither acidic nor basic character. So if we have our pH scale, And it's written with a small p and a capital H. Again, convention. So we're going to make our pH scale. Now the pH scale is a little weird because it doesn't start at 0 just to mess with us. Instead, the pH scale is going to start at lucky number 7. I know, it's a weird one to start at, but that's where we start. And we call this neutral. Now, this power of hydrogen scale is going to extend in both directions now, and each direction will be a different type of chemical. One side is acid, one side is base. 6, 5, 4, 3, 2, 1, and then 0 right at the end. And this side over here, we call this side the acids. On the other end of the scale, we go up, and we go 8, 9, 10, 11, 12, 13, and then 14, way at the end over there. And we call these guys their equal opposites. The base. Plural, bases. It's a weird scale, I know. I mean, it goes from 0, but 0 is not the start, and 15, it's not the end, but 15 would be such a nice round number. It's this way for mathematical reasons. I know, it's a little weird. But let's put some things on here. Let's get a sense of things. And there's some cool stuff to see when we start pulling things out. We'll start with simple. Vinegar. We said vinegar was not very strong. How strong is not very strong? Well, in this case, 7 is water. 7 is good old water, our most neutral of all. So vinegar is right here. Good old vinegar it turns out, is a 3. Seems pretty far from water, doesn't it? Well, okay, let's do some other ones. Coca-Cola. Where's Coke go? All right, well, actually, Coke goes right here at a 2.5. Okay, what else we got? Coffee. Some of you might drink coffee. Coffee's on the scale. Coffee is a 5. Right here. Okay, well that's not, doesn't seem so low. Your hair. Well, those of you with it. Your hair is also on this scale. Your hair is actually sitting at a 4.5, so right here. I know, weird, right? Okay, let's put some other cool things on here. What about milk? Milk is a 6.5. That goes right there, almost at water. Because, of course, well, most of milk is water. I mean, it's only 2% milk, 1% milk. What's the other 99%? It's water. But all right. Enough of this boring stuff. Vinegar, not everyone likes that. Coffee, not everyone drinks that. Hair, probably everyone has that at your age, probably. Coke, okay, that one people like. But let's go with something that almost everybody is guaranteed to like. Chocolate. Chocolate, good old chocolate, is at 5 right here. So those are some examples of everyday objects that you might run into that are pH acidic. These guys are acids in some way. Now, okay, fine, all of these were really boring. They're all like, you know, stuff every day. What about the HCl we used as an example? That's over here. That's over there. It's at 0. If it's 0, don't touch it. That's my advice. A few other ones, maybe one more that we can add on here. 2. Stomach acid. Okay, I think we're starting to see where the line is drawn. Coke, I can drink that. Vinegar, I can drink that. Hair, I could drink, maybe don't drink that. Chocolate, I can drink that. Coffee, I can drink that. Milk, I can drink that. I can drink all of these except the hair. Stomach acid? HCl? Nope. So there's a line here that cuts off at about 2.5. That's where the Coke is. And anything above that seems pretty good to drink. What's going to happen on this side of the scale? Let's take a look, huh? If we're taking a look at the bases, our examples, well, our first one was soap. And soap is right here. Soap is a 9. You could drink soap. I do not recommend it. Another one that you probably have at some point seen, toothpaste, which I've put on 2 lines to make enough space. Toothpaste is an 8. Toothpaste is still pretty bitter. That's why they give it flavors and stuff. And that's why it's sort of, yeah. And you ever noticed how when you take some toothpaste, you brush your teeth, and then you go drink, say, orange juice? It tastes terrible. I wonder why. Well, remember when I was saying about how bases react? They dissolve fat. Your taste buds on your tongue have a coating of fat around them. And when the toothpaste is in your mouth, it kind of thins that coating of fat around your taste buds, which means they are exposed, which means they are vulnerable. And then you put some orange juice in your mouth, which is an acid, and you get a very unpleasant reaction, which of course doesn't taste very good. Now, again, don't worry, it's not like dangerous or anything. Brushing your teeth is still a good idea. I highly recommend it twice a day. It's a pretty good idea, especially after you eat. Before you eat, though, is a little bit tricky because it changes what you taste, because it changes your tongue. Don't worry, it grows back very quickly. Now, okay, toothpaste, soap. Already, these are really unpleasant. Do we have any more examples here? Okay, how about, we'll put one right here. Blood, 7.5. So if you're a vampire, there you go, blood, 7.5. Now you know what it is. It's basic. Why would your blood be basic? Well, remember, bases are caustic. They tend to eat, to destroy non-metals, like living things, like bacteria. Your blood is a huge superhighway. It transports infections all across your body. That's a problem. Your bloodstream doesn't want just anyone hitching a ride. It only wants invited guests. So if you pop in and you try to hitch a ride on the bloodstream and you're an infectious bacteria, the blood itself is already kind of inhospitable. It's not a nice place to be if you're not the right kind of vehicle, the right kind of cellular organism. So we've got these built-in defenses that rely on the pH itself. What are some other ones we've got here? Bleach. You may have heard of it. It's a cleaning agent. It'll take your clothes and make them all white. Or you can bleach your hair, turn it all white. Well, bleach is a 12. Once again, I do not recommend drinking that. That would be bad. Finally, what about that NaOH that we just talked about? Well, you'd think, given that the HCl was 0, you'd think the NaOH would be all the way here at 14, but no, it's actually right here at 13. And then we got one more, which is usually a bit of a surprise. Right here at 8, we got one more cool one. Cocoa. Cocoa. What's cocoa? I don't mean like drinking chocolate. That's usually called a hot chocolate, although you could call it cocoa. This over here is the raw version of chocolate that we harvest out of the plant, and it is bitter. How many people, right, have ever had dark chocolate? And dark chocolate, of course, is very bitter. If it's 100% pure dark chocolate, which you can get, baker's chocolate, for example, that is bitter. Very few people like that. And the reason for that is very simple. Have you ever wondered why a plant grows cocoa, why it grows chocolate? Right? Like, we love eating it, but I'm pretty sure the plant wasn't like, you know what I need to do? I need to become tasty to some very large monkeys. That'll be helpful. No, it didn't do that at all. Cocoa is a poison. Its job is to kill insects that try to eat the plant, much like caffeine. Well, it's super bitter because, again, caustic things eat non-metals. They attack, they destroy living organisms. Now, we can eat chocolate without dying, obviously. Although there is death by chocolate, which is a cool dessert. I highly recommend it if you've never tried it. But we don't always find it very appealing. So what do? We add some milk to it. We add some sugar to it. We process it, and we move it from here to here. you'll notice that there are actually an awful lot of things that we can eat that are acids, right? For acids, we can go all the way down to this level. That's a huge range for acids. But for bases, like, we got this. At this point, it's already pretty bitter. Any more than this, you're literally eating soap, right? And you can get those, the soap-flavored jelly beans and stuff, but nobody really wants to eat soap. And the simple fact is that, as mentioned, bases tend to be caustic towards non-living, towards non-metals, towards living things as a result, because living things tend to be made of non-metals. They tend to be made of carbon, which means that one of the big things, one of the big examples of bases is poisons. A lot of poisons out in the world are made of bases in some way. So as a result, your tongue is very good at detecting bases, because knowing if there's poison in something is pretty important. And then you don't find it very tasty, so you don't want to eat it. Pretty straightforward, right? Of course, over time, people can get used to eating dark chocolate, because with time and experience and practice, you sort of learn that it's not actually going to kill you. We call this having an acquired taste, where something is like, yeah, as a kid, you're not going to like it, but over time, you might decide, yeah, it's not too bad. Chocolate's a good example of this. Coffee, especially very dark coffee, can be like this. Some people might be surprised, because very black coffee can be bitter, but that's not the coffee itself. It's some of the secondary chemicals that are in the coffee. Some would claim that very well-made coffee will not be bitter. It's only when you make it poorly that it'll be bitter. It depends. There's a lot of coffee snobs out there. So some parts of the coffee are acidic, other parts are basic, and you can, depend how you make it. But alcohols and other things are also kind of basic, and they kind of hang out on this side, and they're very bitter as a result, which means that generally speaking, a lot of little kids don't like them. So getting this map of different materials and having a better understanding of this scale and its relationship to people might make a very logical question. What does happen when you mix toothpaste with orange juice? What happens when you mix baking soda with vinegar? Well, I don't have baking soda up there. Baking soda should be, let's see, baking soda should also be about right here. I mean, it's something you can eat, so it can't be too strong, but it's also not something you want to eat by itself, because it's not going to be very pleasant. So baking soda is another 9. So what happens when I combine baking soda and vinegar, right? Because we got two opposites here. What happens when you bring opposites together? Well, they're going to react. The reaction that we're going to get here, we have a special name for it. We call it a neutralization reaction. And it's going to produce something. So we call this neutralization. Basically what we're saying is that, acids are very acid and bases are very bases. But when I put the two together, they're neither of those things. They become more like, water. That's one of our products. We're going to get some good old water in this thing. But then there's one more thing that we're going to get. What happens when you put vinegar and baking soda together? What do you got left over? Well, you've done it before. You've all made the volcano. And there's the bubble and the froth and everything. And then there's something else at the bottom. You look down at the bottom and there will be a solid left over. And that solid is a salt. A salt. What's an example of this? Well, let's do our absolute best and simplest example. Our acid, HCl. We're going to combine that with NaOH. We're going to get water. How are we going to get water? Well, what's water made of? H2O. HOH. Well, that's H2O. It's just written in a weird way. We almost never do it that way, right? We always write it as H2O. But it's basically the same thing, right? We're just combining the H's and the OH's together. But look what's left over in terms of the pieces. We have Na and Cl. Those acids and bases individually would be incredibly dangerous, right? If you touched HCl, you'd have a bad time. You touched NaOH, you'd have a bad time. If you touch salt, you'd probably have a tasty time. Depends how much salt there is. Everyone likes a different amount. You need salt to live. You need water to live. These two, you don't want those anywhere near you if you want to keep living. So a neutralization reaction is about combining an acid and a base. And as we alluded to and as we mentioned, acids have H and bases have OH, at least at grade 10 level. Don't worry, you'll get more complicated later. Now, the other thing to sort of see here about all of this, right, is that this is another reaction for us. This is our 6th reaction. I mentioned that in the types of reactions video. So the acid plus base makes salt plus water. Now the difference can be what type of salt, right? Like instead of me doing a sodium hydroxide, which is what NaOH would be, I could do potassium hydroxide, right? Put a K in there. In which case I don't get NaCl, I get KCl. It's still a salt though. A salt is just what we name it when it's just basically an ionic solid like that, a thing that's made of two, metal and a non-metal. Now, I will mention that HCl does have its own name in the acid-base naming rules. We call it a hydrogen chloride or hydrochloric acid. Hydrochloric is a little different than hydrogen chloride. For our purposes, I'm okay with you using hydrogen chloride. Yes, there is a whole other rules for naming that we could use to name this. We could call it hydrochloric acid. But we don't have to go there because it's just grade 10, so we'll keep it simple. But for those who want to know, there it is. There it is. Right? But for most of us, hydrogen chloride is fine. Now, we now understand the scale. We now understand the range of the scale that we can drink on a regular basis. Oh, about there is what we can handle. About there is what we can drink or eat in some way. And again, toothpaste isn't going to be very fun. We also understand that we can combine these two, and then we make, boom, water right in the middle of the scale, 7. That's all pretty awesome. But how can we identify whether things are acids or bases, right? Like we talked about historically, we tasted them. I don't want you eating anything in the lab, and you don't want to eat anything in the lab. You don't want to put this stuff over here anywhere near you. You don't want to have to do a little bit of a gamble to figure, oh, is this dangerous or not? I better find out the old-fashioned way. You don't want to do that. So instead, after a while, chemists started to discover a series of indicators. Indicators. And the purpose of an indicator is to indicate, because scientists are bad at naming things, it is to indicate if something is an acid or a base. And the way they did that, well, they cleverly pointed out, humans have got pretty good eyes. I mean, mine are pretty terrible. That's why I've got glasses. But most humans have pretty good eyes. We can see incredibly fine detail, and especially we are awesome with colors. So, why don't we make our indicator change color? Now we're talking. So there are a range of indicators that we're going to work with, right? So the purpose of an indicator is to change colors. Goodbye, pH scale. Now, there are a range of different indicators. You are expected to understand roughly how a bunch of them work. You're also, of course, going to work with some of them, see how they work, get a hands-on approach. But first, let's get the list of them. So our indicators are chemicals that react in the presence of an acid or a base, and they change color in some way. We're going to talk about 4 different indicators, okay? Our first one is called litmus. This is the famous thing, litmus, which has the saying that is now used in English. We're going to do a litmus test, which is usually meant to do a small little sample just to get a sense of how things are going. That's where the saying comes from. A litmus test is an actual chemical thing you can do to identify if something is an acid or a base without putting yourself in harm's way. So we've got litmus as our first one. Now, in both cases, we're going to have good old acids. And we've got, of course, bases. So the key here is that in different types of materials, litmus will behave differently. Now, if I remember properly, litmus, I think, is actually a type of like lichen, or lichen as it's sometimes pronounced. like a living thing that grows on a rock, and it just so happens to react to acids and bases and changes in some way. At least that's, I think, the historic start of it. Don't quote me on that one. Anyway, litmus has a certain behavior. Specifically, litmus is usually on a paper, and blue litmus will turn red in the presence of an acid, whereas red litmus will turn blue, oops, almost forgot how to spell blue, in the presence of a base. Oh, I wonder if there's a reason why I was using those colors for everything this entire time. So the thing to remember is that red litmus paper turns blue in a base, blue base. Blue turns red in an acid, red acid. All right, so that's litmus paper. It's pretty good. That's a starting one anyway. But we've got more than that. We can go much further. Now, the problem is the spelling for some of these is a bit of a mess. So I'm just going to check my notes here. The next one is called, I'm not even going to pronounce it. I'm just going to put it on the board. Why am I going to do that? Because I want to see. I-E. Yeah. There it is. That's the word. Do you think you know how to say it? Could you guess? Could you try? It's called phenolphthalein. Yeah, I know. Obviously, this is using a completely different description and naming system than anything else we've seen so far, because it turns out that matter is complicated, and we can't teach you everything in a single 1.5 month period. So it takes a bit to be able to get through everything. So phenolphthalein, in the presence of an acid, is clear. Clear as water. It literally looks like water. But in the presence of a base, it turns pink. A bright, vibrant pink. So you can just imagine it, right? You've got a container, you put a little phenolphthalein in there, and it just suddenly goes poof, pink. That's how you know it's a base. Way safer than trying to drink it. Now, our next one, we're going to talk about something that's going to be called phenol red. Yeah, I know, it was on the tip of your tongue. You had it. You had it. It's phenol red. Phenol red. Guess what color it is in the presence of an acid? Yeah, it's not red. It's actually yellow. And you're like, wait, why is it called phenol red? Because it's red in the presence of a base. Whoops. So it starts red, and when it touches a base, boom, it turns yellow. That's why we call it phenol red, because it looks red to begin with. So phenol red is useful for figuring out if something is sort of going this way, we'll call it, whereas phenolphthalein is actually better at figuring out this way, because it starts clear when you first pull it out of the bottle, and it turns pink in the presence of a base. Whereas this one starts red and turns yellow in the presence of an acid. I know, pretty weird. Then we got another one with a really weird spelling. Ooh, yeah, you know what? You guys have got this pronunciation down at this point, so I obviously don't need to explain to you that that spells bromothymol blue. Bromothymol. Chemistry names are weird. Anyway, bromothymol blue. It's blue in a base, and it'll turn yellow in the presence of an acid. All right, fine, one more. I get it, you want another one. How about methyl orange? Okay, oh, methyl orange. Okay, all of these other ones, red was red and blue was blue. Mr. C's tricky, though. So what's the chances that orange is orange? You know what? Go for it, guys. Trust your gut. Maybe I'm not tricking you this time. Turns out I'm not. This is going to be orange. And when it goes over here and you put it in the presence of an acid, it's going to end up turning kind of a red color. So it kind of does the opposite of this one, where this one's sort of red to yellow, and this one is sort of yellow to red, in a way. Orange and yellow are pretty close. So anyway, these are a series of indicators. There are many others, and to be honest, these all only work to a certain range of pHs, right? We talked about the pH scale. It only works to a certain range of pHs, but I'm not going to go into that much detail, right? We're just going to go very simple. We're going to say if I put phenolphthalein in a base, it'll turn the base, it'll go from clear to pink. We're just going to leave it there. But if you want to look into it in more detail, you're going to find, obviously, that this stuff can get pretty complicated, right? Because, well, it's matter and chemistry, and all these things are pretty complicated. So there we go. That is about the last piece of this whole idea. We have this concept now of an acid and a base, a binary set of compounds, two opposite in their behavior. One of them is sharp and corrosive, and it eats metals, and it's sour. The other one is slippery and bitter and caustic, and it eats nonmetals. One of them we can eat a lot of. The other one, it's mostly made of soap, and we don't want to touch it. In the old days, we used to find out what they were by tasting them. We don't do that anymore. Now we use indicators to figure it out. And we also now have a pH scale, which allows us to work out what's going on, right? We can extend that scale from the bases, the acids, all the way into the bases, because we go from 0 all the way up to 14 with good old 7 in the middle. And we know that the acids are over here and the bases are over here. And that's it. That is the last piece of this course. Now, when you go to eat sour candies, now when you go to drink blood, because you're a vampire, obviously, you will know what you're dealing with. And you will have the ability to test these things, to understand these things, to identify what these things are. And you now know that if you mix that toothpaste with that orange juice, you make water and salt in your mouth, which is one of the reasons why it tastes so bad, because salted orange juice just sounds ugh. And you know a whole bunch of chemistry. Now, you guys have a test coming up. Make sure you've practiced. If you've been practicing this entire time, you should find the test pretty simple. It's just stuff you've already learned. If not, well, you've got some review to work through. See what you can do. The next time I see you, we won't be doing chemistry anymore. We'll be doing something else. Continuing to expand and to climb that mountain of knowledge. But we'll save the poetry for later, and I will see you guys next time.